Stream function. Stream function is a mathematical device which describes the form of any particular pattern of flow. It is shown by Greek letter psi. So this is the symbol of a stream function, so it's called psi. Stream function is volume flow rate or flow across any line connecting point A and B. So in this topic, you must know that stream function or psi here is actually represent the volume flow rate. However, we not use the term volume flow rate, we will use the terms of stream function. Because it carries the same meanings of as volume flow rate, we could write that Q is the volume flow rate is equal to A times V, which is A here is the cross-sectional area and V is the velocity. So we could rearrange this equation as V is equal to Q over A. And to write the psi here, you may write the psi here by drawing like this. So it is okay for you to have something like this, because it's quite difficult to write a psi in by using a mouse here. So it is okay for you to draw a psi is something like this. Okay, please write it properly, because we have another symbol after this that quite similar to this one. So now we will discuss about the stream function for Cartesian coordinates. First, you need to draw this diagram. So this is the Cartesian coordinates. We have x-axis here and we have y-axis here. So we draw a rectangular box here to show the element of fluid in Cartesian coordinates. So we have dy here as its height and dx here as its length or its width for this rectangular element. So we draw a velocity, we draw a u here as the component velocity on x-axis, and we have small v here as the component velocity on the y-axis. As we know, in previous notes, we say that stream function psi is actually the volume flow rate. So we could calculate the volume flow rate. Q is equal to A times V, and then we can rearrange the equation becomes V equal Q over A, and we use the idea to develop our stream function. So for example here, we want to develop what is the relation between the component velocity of u and the stream function. We could write as u equal d psi over dy. Because we are focusing on the component velocity, that's why our stream function here is dy, means a small portion of stream function at this element only over dy means the cross-sectional area go through by this velocity. So here, we have dy, and we assume that its thickness of this element is equal to 1, so it is okay for us just to write dy. So another reason is because in this topic we are focusing in two-dimensional axis, so mean the value of z here is only 1 unit. So if you're still confused by the idea of 1 unit, so you could imagine that the x-axis here, the thickness of this element is equal to 1. That's why the cross-sectional area here will become dy plus 1. So it's dy times 1. So it becomes dy only. So we could write the value of u here is equal to d psi over dy. And then the value of v here is negative d psi over dx, which is d psi here is the stream function for this particular area, and dx here is the cross-sectional. Again, the length here is dx, and the thickness of this element is equal to 1, so it's only show as dx. Because we have polar coordinate later on, so to differentiate between clockwise and counterclockwise motion, so we make a rule which is the counterclockwise is assumed to be a negative direction. So because the v here will create a counterclockwise that motion like this, so negative sign need to be added in this equation because the rotation direction is counterclockwise. Please remember this one. So as a conclusion, the v, the component velocity for y-axis, v is equal to negative d psi over dx. And this is the stream function for the polar coordinate. So this diagram is the representative for the element in polar coordinate. So we have this kind of element. We have the component velocity for radial direction ur, and for the angular direction u theta here. So the length here is r d theta, and the length here is dr, and again we are focusing in two-dimensional axis, so the thickness of this element is equal to 1. We could write ur here is equal to d psi over r d theta. So this idea is totally same with the idea of volume flow rate Q is equal to AV, and then we change it into V equal Q over A. So this is the idea of that one. And r d theta here is the length of this curve of this part, and we multiply it with 1 because the thickness is equal to 1 unit. So we have ur equal d psi over r d theta. And for u theta here, we could write as negative d psi over dr. So again, dr here is the length of this area times by 1, its thickness. And again, to differentiate between the counterclockwise and clockwise later on, if we comparing with a polar coordinate, later on we will discuss about that. So we take the direction of counterclockwise is negative. So in this equation, we need to add a negative sign because the rotation here is in counterclockwise. So the u theta is equal to negative d psi over dr. So this is the streamline or psi, and because it is reflected or it is carries the meaning of volume flow rate, streamline is actually can be proved in experimental work. So this is the very common pictures that you could get in internet, or I think you already knows that sometimes supercars or sport car is evaluated in a wind tunnel, and then we will use a smoke generator to create smoke like this, and the smoke will flow into the wind tunnel, and then it will create a line like this. So this line is actually the stream function or the streamline. So means that the streamline that we will calculate later on is actually can be represented in experimental work. So in ideal flow, so the usage of ideal flow, the important one is we are going to simulate the stream function or the streamline in our simulation machines. So we could have the stream function or the streamline look like this in our computer. So for example, this is a car. We calculate the stream function, the streamline, and we could create a streamline like this, so we could evaluate the aerodynamic of the car, we could calculate the drag coefficient, the lift force, and so on so forth later on. So this is the simulation pictures of the usage of streamline, and this is the experimental work that use smoke generator here, smoke here, to show the stream function. And for example, this one, so this is the experimental using the very simple object. We call it as an aerofoil. So we put an aerofoil in the wind tunnel, and then we use a smoke generator, and we could have a lot of horizontal line, which is the psi or the stream line. In reality, in wind tunnel, showing like this. And then we will use this line as our calibration or our reference. We calculate our streamline by using the psi equation that we have in our computers, and we could draw, or we could have a totally the same line comparing to the experimental one. So this is the stream function or the streamlines that we calculate in our computers, in our simulation, and this is the streamline that we get from the experimental work.